Okay, let's dive right in. We're talking about motion. It's a huge part of your IGCSE physics exam. So today, we're going to break it all down, get you ready, and make sure you walk into that exam feeling like you've got this.
So does the whole idea of distance-time graphs, velocity, and acceleration kind of make your head spin a little? Are you just staring at all these formulas, wondering which one to even use?
Yeah, you are definitely not alone. It can look super complicated, but I promise you, by the end of this, the whole story of motion is going to be way simpler to understand.
First things first, we have to nail this one fundamental idea. Seriously, if you get this right, everything else just clicks into place. So, what is the real difference between speed and velocity?
Speed is easy. It's just a number. It tells you how fast you're going, 30 meters per second, 50 kilometers an hour. That's it. In physics, we call this a scalar quantity because it's all about the size, the magnitude, just the number.
Now, velocity, well, velocity is a bit more of a stickler for details. It's not just how fast, but also which way. So it's got both a number and a direction. Think 30 meters per second north. That extra bit of info, the direction, is what makes velocity a vector quantity.
Let's look at a classic example to make this super clear. Picture a car turning a corner. The speedometer might be locked at a steady 50 kilometers per hour, right? So its speed is constant. But because the car is turning, its direction is changing every single second. And if the direction is changing, its velocity has to be changing too. And that right there, that is a classic exam question. They love this idea, constant speed, but change in velocity. So burn this into your brain. If you change direction, you change velocity. Period.
All right, so let's build on that and move to the next big topic, graphs. Now, don't think of these as scary diagrams. Just think of them as a picture, a visual story of something's journey. All we have to do is learn how to read that story.
The first kind is a distance-time graph. It's pretty straightforward. It just shows how far something has moved away from where it started. You can see distance is plotted on the vertical y-axis, and time is ticking along on the horizontal x-axis.
The second type is the velocity time graph. This one tells a totally different story. It shows how the velocity, not the distance, is changing. Is the thing speeding up, slowing down, or just cruising at a steady pace? This is the graph that will tell you.
Okay, so how do we actually read these stories without getting all mixed up? I'm going to give you two simple keys, two, let's call them hacks, that will unlock pretty much any motion graph they can throw at you in an exam.
That's it. Seriously, just two things to focus on. The gradient, how steep the line is, and the area under the line. If you can remember what these two things mean for each type of graph, you've basically cracked the code.
And here it is. This is the one. The slide to screenshot, write down, stick on your wall. On a distance time graph, the gradient is the speed. Simple. On a velocity time graph, the gradient is the acceleration. And the area? Well, it means nothing for a distance time graph, but for a velocity time graph, it's the total distance traveled. This table is your secret weapon.
Theory is great and all, but let's make it real. How do we actually use these two hacks to, answer a question and get the marks? Let's walk through it together.
So, how do we find the gradient? You've heard it a million times, rise over run. For a distance time graph, you just calculate the rise, which is the change in distance on that vertical axis. Then calculate the run, the change in time. You divide the rise by the run and boom, that's your speed.
And you know the best part? For a velocity time graph, it's the exact same method, rise over run. But here's the key difference. The rise is now the change in velocity. So when you do the math, you're not finding speed, you're finding acceleration, how quickly the velocity is changing. It's that simple.
And what about that area under the line? On a velocity time graph, you just split up the space underneath the line into simple shapes, like rectangles and triangles. Calculate their areas with the basic formulas you already know, and whatever number you get, that's the total distance the object traveled.
Okay, let's use what we've learned on a really common exam scenario, an object in freefall. This is where you can really see the power of these graphs.
So on the left, you see free fall in a perfect world, a vacuum, no air. The velocity time graph is a perfect straight line. That tells us the acceleration is constant. That's g, the acceleration from gravity. But on the right, that's the real world, with air resistance. As the object falls faster, that air resistance pushes back harder. This makes the acceleration get smaller and smaller, so the graph starts to curve and flatten out, until it eventually hits a constant speed, what we call terminal velocity.
And finally,
Let's talk about the common traps people fall into so you can avoid them. Don't lose easy marks. First, don't mix up the two types of graphs. Go back to that cable we looked at. And please always include your units. Meters per second for velocity, meters per second squared for acceleration. Forgetting those can actually cost you marks.
So if you take just one thing away from all of this, let it be this. These graphs aren't just random lines. They are stories. A flat line tells a story of something staying still. A straight sloped line tells a story of constant change. And a curve tells a story of changing acceleration. Your job is to just learn the language so you can read that story. Which leaves us with one final thought. Every journey, including yours, has its own motion graph, right? There are moments of speeding up, cruising along, and stopping. So what kind of story would a graph of your journey today tell? Pretty interesting to think about.